Okay, I think we can start because the last person to join was like 2 hours late last time as well. So yeah, we can't wait for that, I think. If I recall well, we didn't do the confidence intervals yet, right? No, I think we didn't. Okay, so we're going to open this file on Canvas, XMP 2102. Let me see. I think it's in week 3 or 4. XMP. Here it is. All right. I think we did the F test, right? Yeah, we did. I don't think we did this yet. Okay, so we're going to talk about confidence and prediction intervals. And we already talked about this before. Confidence and prediction intervals are two intervals to estimate the interval between which a real coefficient should be between. So you have the B0 or the B1, B2, B3 in multiple regression, etc. And you want to estimate the actual betas with this, so of the population, because we have a sample usually, and of course you have the sample to estimate something about the population. So with these sample coefficients, we want to know how much confidence or confidence there is with how much we predict the actual betas. And there are confidence and prediction intervals, and the confidence interval is to predict a mean, and the prediction interval was to predict an actual value, if we remember. And a confidence interval is always quite small, for example, 1 to 3, and a prediction interval is usually bigger, for example, from -3 to 6 or something. Obviously, that's a bigger interval. Why is that? Because a confidence interval estimates a mean, whereas a prediction interval estimates the thing if you take one person from the population. So it must be much wider to actually include this person. And you can have a 90% confidence interval, a 95 or a 99. Those are the usual numbers, but you can also have different ones. We're going to do a small exercise again. We have the wage, age, and education model. Remember that from last time. And we want to predict the wage of someone aged 30 with education level of 5 and a 90% confidence and prediction interval. Okay, so we are going to our data. Yeah. I don't think this is the right one. Let me see again, because we have to have the wage and the 2102. Is it 2102? Okay, I think I opened the wrong one. Excuse me. I'll open this one. I hope this is... Yeah, this is the right one. So we'll close the other one for now. Okay, we have the W, the age, and the education level, and this is wage. We go to, first we're going to put in some numbers. So you scroll down to the bottom. I think I already said this last time. You're going to have to leave open some things because otherwise it can't sort of predict it. Because if you already fill it in yourself, then SPSS won't do it for you. So if I recall well, we had someone with the age of 30, someone with an education level of 5. And we don't know the wage, so you don't fill that in yet. You go to analyze, you go to regression, go to linear, as we always do, and you put the wage on the dependent and the age and the education level on the independent. Okay, we have that. Then we go to statistics. No, we go to save. And we want to have the unstandardized predicted values. Remember, we always take unstandardized, not standardized. That's just the way of doing in this course. And we want the predicted values because they asked us for it. It was asked the predict. So we want to predict the wage. So of course we have to tick the predicted values. And we want a confidence and prediction interval with 90%. So you tick mean and individual under prediction intervals. Individual is for the prediction interval, mean is for the confidence interval, and this has to be 90. Click on continue, click on OK, and you should get an output. Our prediction for someone with an age of 30, education level 5, is that he has a wage of 27.563 if you round it off. And there are four rows here, and this is a lower bound and an upper bound, lower bound and an upper bound. So you know those belong together and those belong together. And then this is of course the small interval. So it is the confidence interval. So we have 90% confidence that the population mean is between those two. And we have 90% confidence that the actual population coefficient, if you draw like one person, is between those values. So obviously this is a lot bigger than this. And you also see that the prediction lies within both of these intervals. Of course, that must always be the case, because if it's out of it, then either you have a wrong confidence interval or prediction interval, or your predicted value is wrong, because if those are don't include it, then it would be weird, right? Okay, so that's that. And we already did this. I already showed you. We go to chapter 21. So we used the F-test to test if all the variables were jointly useful. Let me, by the way, look if the other person wants to get in. I think, no, not yet. And we used the F-test to look if all those variables were useful or none of them was useful. But we might want to test if only a subset, so a few of those variables, are jointly useful or useless. And we use something what's called the partial F-test. And you already hear it in the name. Partial is only a part, so you're going to test a part of it. And let's say that the complete model has k independent variables, which we already knew, right? So this goes up until including k. That's why you reduce n minus k minus 1. That's obvious. And we call that our complete model. That are all the, it includes all the variables that we have. And then we have the reduced model, which has g independent variables. So it has less, because g must be less than k in this case. We say that we leave out a few variables in the reduced model, thus the reduced model has less variables. And the partial f-test is useful because it can test if the variables which are left out, so here I have g, here I have k, and what's in between those, so which are left out in the reduced model, you can test if those are useful or not with the partial f-test. And those are the k minus g variables. So here I have g, here I have k, what's in between is k minus g. So that's g plus 1, g plus 2 until xk, which you have left out. All right, okay. So the hypothesis, it looks like the f-test, and it's almost the same, except for the fact that you don't test b1 up until including bk, but you test bg plus 1 until beta k. Because you want to test the reduced model, which was k minus g, so that's g plus 1, g plus 2, g plus 3, etc. until k. And in the first hypothesis, the null hypothesis, of course, you always say those are 0. And in the alternative hypothesis, you say at least one of those is not 0. And I always find it extremely useful to write it down this way because it is the fastest. And you can also write down at least one of beta g plus 1 and or beta g plus 2 and or beta 3 g plus 3, etc. And or between those is unequal to 0. But if you have like 15 of those variables, it's going to take some time. So I would recommend this way. At least one of beta j isn't 0, with j being k, g plus 1, g plus 2, etc. up until including k. So you don't have to include all those here because you can just write dots in between. And for example, if the complete model has 5 variables and the reduced model has 3 variables, remember that we are testing what is in between those. Thus, the null hypothesis should be beta 4, beta 5, both equal 0. And the alternative hypothesis, at least one of beta j is unequal to 0, for j is 4 and 5. So here you also see that it is not the reduced model that we are testing, but it's what we are testing is like what is off from the reduced model. So what it reduced by, that's what we are testing. And another way of stating the alternative hypothesis is like this, like I already said, but if you have many variables, it's more complicated. If you have any questions, you can interrupt me. So the reduced model, remember that we had the f-test, which was, let me look it up, which looked something like, if I can find it, because the partial f-test looks a lot like it, so I wanted to show you. Here's the f-test. The f-test, the normal f-test, so not yet the reduced or the partial f-test, was the SSR divided by k over SSE divided by n minus k minus 1, with k being the degrees of freedom of SSR and this being the degrees of freedom of SSE. So if we have the partial f-test, then the reduced model has a sum of squared errors of SSE R, which stand for reduced. And the complete model has a sum of squared errors SSE C. That's just the normal SSE, but because we differentiate between the R and the C, you have to include the C. But usually this is just of the entire model, which is also in your output if you are modeling it normally. And by adding more variables to our model, we always reduce the sum of squared errors. Thus, SSER of the reduced model is bigger than SSE of the complete model. That's because if we add more variables, the sum of the squared errors becomes smaller. So the complete model has more variables, so it must be smaller than the reduced model. And if this decrease is very big, so going from the reduced model to the complete model or the other way around, if this difference is very big, then the new k minus g variables are useful, because then they explain a lot in the variation of y. And if it's very similar, so the difference between those is very small, then the new variables are not very useful. So we just looked at the F statistic again, and in the F statistic it was SSR over K and SSE over N minus K minus 1. And in fact, this is very much like it, only that the bottom side is actually the same. It's still SSE over N minus K minus 1. You add the C to differentiate between the SSER and the SSEC, but this is still the same in fact, because in the F model, we also used the SSE, and we didn't include the C because we didn't have to differentiate between them yet. But the SSEC is actually the same as the SSE in the F model, which was not the partial model. And at the upper part, we have the SSER minus the SSEC. And this is the reduced model, I would say, because this is the one of the reduced model, which of course is smaller, and we take off the SSE of the complete model, which is smaller, so this should be a positive number, and we divide it by k minus g. And why do we take k minus g? Because k minus g is the degrees of freedom of the reduced model. That is because you have k variables in the complete model, you have g in the reduced model, and what is in between those, thus the subtraction of k minus g, is the degrees of freedom which you have in the part that you left out. So this is the degrees of freedom, not actually of the reduced model, of the left out part, I would say. So that wasn't. If you understand this, if you don't, please ask, because this can be a bit confusing. Again, learn this formula. There is, you can see sort of the why it is written like this. So this is the same, and here you use the reduced model. Thus, the degrees of freedom must be k minus g, because it's the in-between. But you really just must learn the formula. And then, of course, this is again written like this, because the first, you always write it with the degrees of freedom. So the statistic of F, first degrees of freedom is k minus g, and the second is n minus k minus 1. All right. Again, we have the 5 steps. You have the first one, the null and the alternative hypothesis. This is the critical value method, and this is the p-value method. And of course, first steps are always the same. Second step, form the test statistic, is also the same. Here there's again no hinge, as there was not in the F test, the normal F statistic either. So you just write down this entire thing. You don't have to include the part after it. You may, but I never did, and you also don't have to. And then in step 3, for both of them, you calculate F, the realization of the test statistic for both of them. I'm just going to take a sip. And in step 4, they will become a bit different again. The steps, by the way, are always the same, but I'm just going quickly over them to have you to remind you of them. First, in the critical value method, which is on the left, you reject H0 if the realization, which you calculated in 3, is bigger than or equal to the critical value. And here they wrote it wrong. I noticed that. I didn't even notice it when I was learning myself. I noticed it this weekend when I was making the PowerPoint. There should be alpha k minus g instead of just k. And it's a mistake in the slide. So always write down alpha k minus g and minus k minus 1. Here they wrote it correct, by the way. And you can find it in Excel with just the normal F. So you don't have to write F partial or something. And why don't you? Because you already include the different degrees of freedom. So you sort of are doing it yourself. And that's, of course, very useful because you need to remember less. Again, be reminded that the F-test is always and only upper-tiled. So you only have to test an upper-tiled test. That's why there isn't included a lower-tiled or a two-sided test here. And in Excel, you use f.inf. Remember, you always use inf for the critical value method and dist for the p-value method. And you use f.inf 1 minus alpha if your alpha is, say, 0.05, because we always calculate it to the left of the graph. I've said it, I think, multiple times now. And so because it's an upper tilt test, it should be the graph to the left, and there's only a very small tail at the right. So it should be like something 0.95 here. So 1 minus 0.05 is 0.95. Here you have k minus g. If your k is, say, 6, so you have 6 variables, and your g, so in your reduced model, is 3, then you get 6 minus 3 is 3. And for example, if your n is 150 and your k is 6, you get 143 here, because you have to include the minus 1 for the b0. And then you draw your conclusion. So if the F statistic or the realization of your F statistic is more than your critical value, then you reject it and you tentatively accept H1, which means that your model is useful. That was the conclusion that we could draw from this. And if you do not reject H0, you are not sure whether it's useful or not. And you cannot say it's not useful because you don't accept H0. If you had philosophy of science, I think we all know this. But to be honest, that doesn't usually come up in a test because it's more philosophical than mathematical or statistical. Then if you have the p-value method, the first 3 steps are the same, and you reject H0 if your p-value is less than your alpha. So the chance of finding this hypothesis under finding this finding under the hypothesis of 0 is so small that you can reject H0. And you do this in Excel again with f.dist. and you take the 1 minus, because you get an upper. It's an upper-sided test, and you want like what's in the tail, but it always calculates it to the left, like I said. So you have to do 1 minus what's to the left, and then you'll get what's in the tail. Again, you always take the value of your F statistic first. So you fill that in, and then it calculates what's on the, usually what's on the right, but because we do 1 minus, usually on the left, sorry. But because we do 1 minus it calculates what's on the right. And you fill in your degrees of freedom, k minus g, n minus k minus 1. And of course, true, because we have a cumulative distribution. And if you would fill in false, then it would calculate sort of a very small bar, which we don't want, because that's like at one point, but we want the entire distribution under the graph. And then you draw a conclusion. So if your p-value is smaller than your alpha, then you reject H0, because it's so small that you find this F value under H0 that you can reject your H0. Okay, I think we're going to do an example now. Are we not? Yes. So one way of doing a partial F-test is by first estimating the entire model, then your reduced model, and then look at the difference between the outcomes of adding some extra variables to your model and their effect. But I think this is very complicated, and it goes wrong often in my experience. It is included in the slide, but if you know the methods that I will tell you now, you will actually never have to do it. And I think this method is a lot easier, and it's less prone to mistakes, I would say. So we can also get the partial F statistic directly without a calculator. And assume you want to analyze the addition of the number of people in a household and the number of children, in addition to household income, and how it influences household clothing expenditure. We have to open a new, the new document, which I had before, so I was one step ahead, I think. Now it is 21.02. And I'm going to close the other ones because I don't need them. You can save them if you want. I've saved most of them, but because I'm doing them now for the third time or something, I don't save them. But I do recommend you, if you, for example, try an exam, to save your outputs, so you can always look back what you did wrong or what you interpreted wrong. Okay, so here we have the document XMP 2102 SAV, which you can find in week 4 or 5. And we have clothing expenditures, HINC, which is household income. I'm not, by the way, making this up. I just, in a question, they always say which one is which, but I just remembered. And usually the names are also obvious. And kids, and usually stands for the number. So number of kids and household size, HS. What did they want from us? Let's look at the description again, because this is really where you are going to find out whether you have to which you want to put in the reduced model and which you want to put in the complete model. So assume you want to analyze the addition of number of people in a household and number of children, in addition to household income, and how it influences household clothing expenditure. So the entire model would include the number of people in a household, number of children, and household income. And of course, the dependent variable would be household clothing expenditure. Because if there are more people, if there are more children, and if there's more income, I would say usually there is a higher household clothing expenditure. How are we going to do this? You are going to go to, let's see, regression again. It's always the same for regression. You go to linear and you put in the, I think the clothing expenditure was the dependent variable. And in the first box, you're going to put in the reduced model, which was household income, I think. Let's look again. Yes, in addition to household income. So we already have household income. So we put that in the first one. And then what you're going to do is you are going to click next. And then you add all those variables. So you add household income and kids and household size. So you add the complete model in the second box. If you go to previous, this is block 1 of 2. So this is the first block where you have added the reduced model. And here you add those two, and kids and HS. You have the entire model. And under save, no, it's not save, sorry. I very often forget which one I have to tick, but it's not very important, and as long as you can find what you need. You are going to tick statistics, and under statistics you will tick R-squared change. Why do you need to tick this? Because actually R-squared change has nothing to do with the R-squared or the coefficient of determination. I don't know why it's called like this, but what the R-squared changed is going to say, it's going to look at the difference between the models and the explanative power. So yeah, in that way it does have something with the coefficient of determination, but you don't need it directly for that. You're going to click on continue. And you really have to remember that you always have to tick R-squared change if you want to do the partial f-test, because otherwise you will not get the output correctly. Or you will get the output, but you won't get what you need to answer the question. And you're going to click on OK. And you get a beautiful model again. And what you're going to need is the model summary. And here is our model summary. You, by the way, don't really have to know, like, then I need the model summary, and then I need ANOVA, then I need a coefficient table, because you always get all of them, at least I do. I know a few of you, I know if you have like Apple or a MacBook, or sometimes you have to tick other things. I don't know about that myself because I have an HP or a Windows computer, and so that's a bit different. But I think it was said a few times in the slides or in the lectures. Yeah, but to be honest, I can't help you with that because I don't know myself. Okay, so we have the model summary, which is here, and we have 1 and 2. Why do we have 1 and 2? Usually we only have 1. We have 1 and 2 because we entered more than one model. First, we entered HINC. You can see it here, which was the reduced model, and then we entered HINC and kids and HS, which was the complete model. And what we are going to do is, here's F change. Remember we looked at F change before, which was just your F statistic, and you have 2 of them. And if you do it correctly, the way I did it, so you always, in the first one, you add the reduced model, and in the second one you add the real or the entire model, sorry. There are other ways, by the way. I think in a tutorial they once did it differently, so you can do it differently, but then you have to do it entirely differently. And I think the way they did it is more complicated, and this is how they do it in the slides, like I do it. And this really is the most intuitive format. So I recommend using this one. And you look at the first one, here there's a very big number in the F change. Our F change was our F statistic, if you remember. But this is very big. What does it mean? It means from going from no model to the reduced model. And that's a very big change. So Hink obviously has a very large influence. And the second one is the F statistic if you go from the reduced model to the complete model. So that's 11.1.42. That's still quite a big F statistic. So probably this is going to be so far to the right of the normal graph that it will be concluded that those are or that the added variables are useful, but of course we have to test that. So we will see that in a second. And here is our significance, which we already see to be 0 for both of them, probably also aiding to significance for both of these variables. All right, yeah, so this is what we did. Those were the steps. And I will make this bright red because this is very, very important. So what you do, and I've said this 2 times already, I think, in the first, you add the reduced model, so Hink in this case, and in the second, you add the entire model. There are other ways to do it, which are more complicated, and if you know this way, and you can always do it like this, it should be correct. Please be notified that this is quite a difficult test, I have to admit, and you cannot just assume that you are able to do it in a test, so practice it a few times. And I have done it wrong myself quite a few times. In fact, I had it wrong here as well, so I got another answer than in the slides, and I did something wrong. So yeah, it happens quite often in this test. Doing the F test continued, so we have the model summary, which we discussed, the F change, and we discussed this as well. Okay, so let's see if it's significant. So this is our F statistic, which is 11.142. And this is our significance. Well, we can already probably see that they are significant, but we can test that. So we're going to go to Excel. I know some of you might not have Excel. I think there are other programs. You can also do the F and the T testing in SPSS, but to be honest, I never did that myself because, again, it's more difficult. But there is a very good video on Canvas. If you scroll down on the statistics course, you can find it. And so if you don't have Excel, there are other ways to do it as well. But I'll be doing it in Excel. We type is and we type f.inf for our critical value. And first we have to put in the alpha, which I think, I don't know if I mentioned it. No, I didn't. But we are going to take 0.95 because if I take an alpha of 0.05, then the probability is going to be 0.95. Our first degrees of freedom was k minus g. Let's look at it. So in the entire model, I have 1 variable. Here I have 3. So 3 minus 1 will be 2. It should be 2. And then I have n minus 1 minus k. And I can look that up in the table. under your residual. So it should be 298. Is that realistic? Scroll down a bit. You see 300. 296, sorry, I looked at, this is of course of the reduced model, and you have to take n minus k minus 1 of the entire model, so it should be 296. Okay, 296. You get the output, and you have an F statistic of 3.026, and remember, what was our F value? It was 11. So obviously 11 is a lot higher than what it should be to already reject H0. So you can reject H0 and conclude that at least one of those variables, NKIDS and HS, are useful, are jointly useful. And then if you do the p-value method, which is also possible, you take f.dist, and you have to do 1 minus it because it's an upper tilde test. You take your x, which was something like 11, but I'll look it up. Oh, click it a few times, Control, copy. You're going to paste it, and then it's going to ask for your degrees of freedom, which we calculated to be 2 before, if I recall well, and this is 296. True. And then, as you see, it's very, very small. I didn't have to calculate it myself because it was already here. So here you see that it's very, very small as well. And it's probably a bit different. No, it's actually the same. Here it's 2.2 to the power of 1, 2, 3, 4, 5 minus 5. So 2.2 times 10 minus 5. And here it's 2.16, which would be 2.2 rounded off. So you don't have to calculate it in Excel for the significance level, but you can always do it to check it or something. But you don't have to. I just wanted to show you how to do it again. Okay, let's continue. So we have a bit of a problem because the partial F-test has determined that NKIDS and HS are jointly useful in the model, like we did in the previous slides, because we rejected H0. But looking at the p-values of the significance test in the regression output shows that neither NKIDS nor HS variables are individually significant. So let's look at that. Here was our output, and if you go to the second model, which was the complete model, you look at NKIDS and HS, and they both have a very high significance level, so 0.4 and 0.3, and usually you have a significance level of 0.05. So obviously you would not reject H0 here. So both of them are not statistically individually significant, but they are jointly significant. And why is this then? Well, it's because of something that we call collinearity. And if you would calculate the sample correlation between NKIDS and HS, we see that it is RXY 0.927. Remember, the correlation is how much, if one, for example, goes up, how much the other one goes up. And this is a very high number. The sample correlation is 1 at its maximum. So obviously this is very high. And that means that they are highly correlated. Is that a problem? Not necessarily, but you have to take notice of it. And why are they related as such? That's because if there are more kids, usually the household size is also bigger. Unless if you get one more kid, you get one less adult. But usually I think it's obvious that if you get more kids, your household size also grows. So there is a strong correlation between X variables, and we call this collinearity. I'll make it red, so you know it's important. So when two X variables are strongly related, either negatively or positively, so close to 1 or -1, we encounter collinearity. And strict collinearity is when one of the variables is a linear combination of other independent variables. So for example, if there was another variable x4, which is the number of adults, and then it holds that x3 is x2 plus x4, x2 being the number of children and x4 the number of adults, and x3 is the household size. So obviously the number of children plus the number of adults is equal to the household size. So household size is actually a linear combination of the other two. And that can be a problem because SPSS will automatically remove one of them because it sees it as redundant. Because you can just count those up and you already have this x3, so you don't need to include the x3, or it will say you don't need x2, because if you take x3 minus x4, you will already get it. So it will actually delete it himself, which is not a problem, by the way, because you can still do all your calculations, but SPSS will just see it as redundant. So you can take like 2 hours filling in an entire data row or anything, and then SPSS will delete it because it doesn't need it. And collinearity is when they are strongly related, and it's not the same as a strict collinearity. That's when they are a linear combination, but collinearity is when they are strongly related, such as was the household size and the number of children. Because it could be indeed that maybe an adult leaves if one more child comes in, but usually it doesn't. So it's not, the relationship isn't 1, but it's close to 1. What's the consequence of collinearity? It can make the interpretation of beta j difficult, so of the coefficient of any variable, because, for example, with the child example, it is unclear if it's the children that increase expenditure or the household size. And collinearity also increases the size of the estimated standard errors. Again, you don't need to know why, you just need to know that it does. So it has 2 consequences. It can make interpretation of our estimated beta j difficult, and it increases the size of the estimated standard errors. And if the standard errors are bigger, then our confidence intervals will be bigger. And this makes p-values from significance tests larger, such that then if p-values are larger, the chance to reject H0 is smaller, and thus it can be a problem in testing. You need to just remember those 2. This is very obvious. We don't get a clear explanation for the second one, so you just sort of need to learn it, I would say. Okay, then we have non-linear relations. So we said until this far we've only had linear relations. For example, y is beta 0 plus beta 1x. But there can be non-linear relations, so when the line isn't a straight line. And we can have a quadratic function, as such is here. So this is not linear anymore, because for bigger values of x, the y increases more. And if we didn't have this squared power, then it would be linear. An example, as x changes, this becomes, if it's 0, it's beta 0. If it's 1, you get beta 0 plus beta 1 plus beta 2, because you fill in 1s here. But if it's 2, you get beta 0 plus 2 beta 1 and 4 beta 2, because this is quadratic. So it gets quite an increase if you go up with a small step. So the increase is smaller, is bigger than the increase in steps. So as x goes from 0 to 1, it increases by beta 1 and beta 2, obviously. And as x1 goes from this one to this one, it increases by 1 beta 1, because you had 1 beta 1, now you have 2. So you get an extra beta 1. And it goes from 1 beta 2 to 4 beta 2s, so you get 3 beta 2s. And the change, of course, depends on the value of x. If I fill in a value of 9, then of course this change is going to be very big because it's quadratic. That's the first nonlinear relationship. There's a second one, and that's with interaction terms. So when, for example, x1 and x2 interact, this is called an interaction term. So when you multiply two variables with each other, yeah, the other person still isn't joining. That's bad, but okay. So we call this an interaction term. And why do we add an interaction term? We add it because you expect the relationship between y and x1 to be different for different levels of x2. So for example, if you take y to be wage, and you take x1 to be age, and you take x2 to be education level, of course, if the age goes up and the education level goes up, then wage goes up. But there might be an interaction between the two, such as that when the age goes up, the education level might also go up, which is quite obvious because usually if you go from being 10 to being 20, probably you also have higher education. So there can be sort of this interaction term where they interact. And that's why you include this one. You don't usually have to come up with those yourself. It will just be said and interact, for example, this variable with this variable. And you'll just do that and you'll be fine. You do need to make them yourself in SPSS. So how are we going to do that? We still have this model, I think, of clothing expenditure, household income, number of kids, and household size. So let's see what we have to interact. That's always given. We want to, okay, here's our model, and it's given. So like I said, that's easy. Household income, okay, that's x1, and household size is x2. Okay, so we want the square root of household income, and we want an interaction term of both of them. So we want household income squared. If you look into your data, you only have household, this HS, household size. And you only have household income. You only have number of kids. And we wanted, if I recall well, I always forget, we want the household income squared, but we don't have that. So we're going to have to make that ourselves. You go to transform, you go to compute variable, and here it is. And then you put hinc in here in the numeric expression. So you can do that. You can drag it. Now I have it twice. Or you can just put it with this. If I get it here, you see you can put it like that. Okay, so we have the hinc here and we want it squared. There are a few ways to do this, I think. I usually just do it times itself. I know there are other ways. I think you can do it with a 2 as well. I think you can also do it with this multiple thing. I think you should be able to, but I never really trust those things. So I just do it times itself. You have to give it, on a target variable, you can give it a name. So I call it hinc SQ for squared. click on OK. And if you go to your data, you have a new variable, and that's Henk Sku. So this is, if I'm correct, if you multiply this with itself, you get this number. Let's see if it actually works. Control copy. We'll just quickly check it in Excel, because why not? Times itself. Yeah, that's correct. 421. So that's our first variable. And we also wanted to interact household income with household size. You go to transform again, compute variable, reset it, and for example, you call it interaction. Oh yeah, always do this in caps. Otherwise, for me, it doesn't work. In some computers it does, but in my computer it doesn't. Interaction, Henk, and household size. I always get like really large, there's very large names. You can also just do Henk HS, maybe that's easier to see. So you put in Henk, you put in the little star, the asterisk, I think. You do it times household size, if I recall well. Yeah, and you click on OK. Always make sure that at least you multiply the correct ones with the correct ones, because if you go wrong there, your entire model will be wrong, and that's really a waste, because this is like an easy step. The rest is a lot more difficult. So make sure that at least you do this right. And we get this number. And we have then gotten our transformed terms. And then if you want to make the model, you go to Analyze, Regression, Linear. You're going to reset it because there are still those two blocks and stuff. Click Reset. Loading expenditures from the dependent variable. Henk is here. Household size is also here. This one is here. And this one is here. The way of which you put them in doesn't really matter. But I usually just throw them in. But if in the model it says, for example, I think it said that household income should be x1, then if it asks for the coefficient of x1, it might not be beta 1 in your own model, because now I've just randomly thrown them in. So you always have to look at that well. For you guys, I will do it correctly now, because you might get confused. So we'll do it in the right order. So what did it say? It said household income first. Then it said put in the household income squared. I think then comes household size. And then comes your interaction term. If you click on OK, now it should be in order, I think. Yeah, now it's in the same order as it is on the slide. So that's the easiest, but if you don't put it in order, make sure to check which one is which, and that you get the coefficients which are from the model. So now Henk is beta 1, but if I had put it down here, then for me it would be beta 4. But if in the model it says it's x1, then you should call it beta 1, obviously. But just be reminded of that so that you don't make mistakes there. Okay. I think we can take a small break, and we'll be back in 10 minutes, so a quarter past. And then we have to do 20 slides, and you can ask questions if there are any. And if there are none, then we can start on an exam together. We probably can't finish it, but yeah, we can at least start it, and I would show you how I would take it on. I've chosen for the exam of 2019 the Resit because that's the one that you can do in Canvas. So you also get used to that. But now we can take a small break. So I'll see you in 10 minutes.